All right, ladies and gentlemen, welcome back to another video with Mr. Kenton, AP Chemistry. We're continuing our discussion through kinetics, and we're going to be looking at topic 5.3 within AP Chemistry, which looks at concentration changes over time. Now, again, I know we've already done this, so I can hopefully be a little bit more concise with my video. So let's go ahead and just dive right in and kind of go from there. So remember, we talked about this in class that, graphing the concentration of a reactant versus time is going to allow us to deduce the reaction order as each order produces predictable curves on a graph, right? So this is different from just taking a look at experimental data where we're given data tables that have different experiment numbers. We get the concentrations of reactants and the reaction rate, and then we try to deduce it from there. Here, we're simply given the graphs, and we're going to be asked to say, okay, because I'm seeing this particular line, curve, or shape on my graph, I need to be able to identify it as either 0th, 1st, or 2nd order, right? And so by plotting a graph of concentration of a reactant against time, we can see trends and identify the reaction order, right? And so, like what we've got here, and we'll see how we can use this particular graph with respect to half-life to determine, the blue line is 0th order, the red line is 1st order, and the yellow orangish line is going to be 2nd order. And so that's really going to be the bulk of what this video is going to look at how do we use these graphs to make those predictions and identify the reaction order. Okay. Now, again, our goal is we need to be able to take the rate loss. So we learned about in topic 5.2 how we could produce a rate law for a given reaction, for a given component, for a given process, right? And so, and we even looked at how once we had that, we could figure it out as at any different concentration, it didn't matter, right? And so what we want to be able to do is take our rate law, convert it into a convenient equation that's going to give us concentrations as a function of time, right? And so for our purposes, we want to use the equation of a line, y equals mx plus b. And so our goal is going to be taking those rate laws that we have and converting them to a useful expression that can be used to solve for those concentrations. So for first order, and if you recall, we said that the natural log of the concentration of A at some time t is equal to negative kt, so negative k times the negative rate constant times the time, plus the natural log of the initial concentration. That's going to be our slope-intercept form of that equation, right? That's our y equals mx plus b. Now again, our bracket AT is going to be the concentration of A after some time t. K in this case is the rate constant. Because it's first order, it's going to have units of inverse seconds. Our time in seconds, just please keep in mind the time could be in different units. I'm using seconds because that's what's most common. And then A naught is going to be the initial concentration of A in your given process, right? And to really drive this point home of how we could set this up as our kind of our slope-intercept form, right? Our y term is going to be the ln of AT component, right? The negative KT component of this expression is mx. And the y-intercept is ln of A naught, which is going to correspond to our B term in our expression. Now, if a reaction is first order and you plot the natural log of concentration with respect to time, if you end up getting a negatively sloped straight line, then you're going to be able to communicate and be able to deduce that that process is going to be first order, right? However, if you plot ln of AT with respect to time and you get something that is not a straight line, or it's a straight line but has a positive slope, then that means that it's not going to be first order, right? So the line is going to have this sort of representation. Is it going to be this exact line? No. But when you plot ln of AT versus time, if you get a negatively sloping straight line, with those particular data points, that means you have a first order process. All right. Now, here's just an example of just plugging in information. It's a lot of repeat information from the previous slide, but I think it's good to take a look at, right? So we've got ln of y is going to equal negative 2.5 times 10 to the negative fourth times time plus the ln of 5.00. So looking at how we've plugged that into the expression, 2.5 times 10 to the negative fourth is the value of k, right? That's our rate constant value. ln of 5.00 is our b value, right? And then the initial molarity is 5.00. Now, we've seen how y equals mx plus b looks very similar. It can be arranged in such a way that that equation looks this way. On your reference sheet, the only thing I'll mention here is that you're going to be given this expression on your reference sheet. So notice that the only difference there is that they've subtracted over the ln of the initial concentration. So all you would have to do to get it back to the slope-intercept form would be to add an ln of a naught to both sides. Okay? All right, and so here is an example. Here's what that graph would look like if we had that first order process, right? So there's our slope. We've got our ln of 5.00. That's going to be at 1.61. And we've got our negatively sloping line. Now, if our process is second order, the rate law can be expressed in our slope-intercept form as 1 over the concentration of A at some time t equals the rate constant times time plus 1 over the initial concentration, right? I'm not going to spend as much time going over what each of those variables mean. The only thing I want to pause and take a look at here is that because we're dealing with a second order process, ladies and gentlemen, that means the units for our rate constant are going to be inverse molarity, inverse seconds. Those are going to be multiplied together. So you could think of it as 1 over molarity times seconds. Again, time is in seconds, but time could be in another interval, whatever they communicate to you in your problem. And then your A naught's your initial concentration. Now, again, this equation has the general form for a straight line, where our 1 over AT term, that's y, KT represents mx, and then 1 over A naught is the y-intercept, which is our B component within our slope-intercept form. Now, if you were to plot on a graph the 1 over concentration with respect to time data, and you end up with a positively sloping straight line, then what that's going to communicate to you is that you're going to have a second order process. Okay? If, for whatever reason, you graph 1 over AT with respect to time, and it's got a negative slope, or it's curving, or something like that, that's going to communicate to you that it's not second order. Okay? So paying attention to the units on your graphs and looking at the lines that they produce is really important here. Now here's an example. You've got 1 over z equals 2.5 times 10 to the negative fourth times time plus 1 over 5. So again, 2.5 times 10 to the negative fourth is the k value. That's our slope. 1 over 5 is our b value, and 5 is our initial molarity. We've got it written where we can see here's our slope-intercept form. Here's that expression written in slope-intercept form. And then if you look at your reference sheet, the only thing that they've done is they've subtracted over the 1 over A naught term. So if you wanted to get it back to that slope-intercept form, simply add the 1 over A naught to both sides. And again, this expression that I'm kind of circling around right here, that is provided to you on the AP reference sheet. Okay, and then there's what that graph would look like. Again, 1 over 5 is 0.2, so we've got our starting point, our y-intercept, and then it's got a positively sloping line, and that would indicate to us, because we've got 1 over z versus time, that this is second order. All right. The last thing we've got to take a look at is zeroth order. Now, if you remember, if something is zeroth order, that means changing its concentration doesn't impact the rate. So if you have an overall process that's zeroth order, rate is simply going to equal the rate constant, right? So if rate doesn't change with concentration, we can then get an integrated rate law where we have the concentration of AT equals negative KT plus the initial concentration. All right. So again, those variables, all the same that we've seen. The only thing I want to hone in on is that for a 0th order process, the units of the rate constant K are going to be molarity per second. Because of rate equals K, rate is in molarity per time unit. So that's why K is going to have units of molarity per second. Time in seconds, and then A naught's our initial concentration. Again, this equation also follows our slope-intercept form. Y is going to be represented by AT. Negative KT is mx, and the y-intercept B is going to be represented by the initial concentration A naught. Now, if you plot concentration versus time data, like we see here, so concentration is on your y-axis, time is on your x-axis, if that gives you a negatively sloping line, then that's going to communicate to you, ladies and gentlemen, that you're going to have a 0th order process. Okay? Now, if you plot this data and you get something that's a positive sloped line, or if it's a curve or anything like that, that's going to communicate to you that it's not 0th order. All right? And here's our example. So you got concentration of x equals negative 2.5 times 10 to the negative 4th times time plus 5. So again, our 2.5 times 10 to the negative 4th, that's our value of k, that's our slope. 5.00 is our y-intercept, and 5.00 is also our initial molarity. Again, we've got our slope-intercept form of this equation. What you are provided on the AP reference sheet is this expression, that the concentration of AT minus the concentration of A naught equals negative KT. So you're given this. If you wanted to get it to this form, simply add to both sides a positive A naught. It'll cancel out on the left, and then you're back into your slope-intercept form. Okay. All right. And so there's our graph. So we started at 5. It's got a negative slope, and it's going to be decreasing of that value over time. It's got concentration on the y-axis, time on the x-axis. So this would communicate to us that we have a 0th order process. All right. Now I know that we worked this out in class. I'm not going to go through kind of the depth that I went through it there, at least in this video. Maybe I'll make a separate video where I do that. So something you could be asked to do is say, okay, with the data that's been provided here, determine the reaction order and then calculate the value of K with units. So we've got our reactant, we've got our products, and so what they give us timestamps, and they give us concentrations over those timestamps. And so remember, our task is going to be, we need to check to see, is this going to be a 0th, 1st, or 2nd order process by graphing that. So they've given us the information so we could set it up for 0th order. We would then have to go through and plot the data for something. We would have to do the ln of this data as well as 1 over this data for 1st and 2nd order respectively, right? And so when you do that, you get the following 3 graphs, right? So with the concentration versus time data, we see that the blue line represents what we get, and kind of the light blue line that's in the background is what we would be looking for. So we know that with respect to 0th order, that doesn't match up. We look at the natural log of concentration versus time data, right? So we see that it's got a negative sloping line, which matches up with what we should see with 1st order, and we're not seeing any deviation from the straight line that we should find. So it's looking pretty good for 1st order. We check our 2nd order graph, which is our 1 over concentration versus time. So we've got our dark blue curve represents the data that we have, and this represents the line that we should have if it were 2nd order. So we're seeing that there's a deviation there, and so it can't be 2nd order. And so then what you could do is, if you got this plot in your calculator, you could perform a linear regression to calculate what the value of the slope of that line would be equal to. And so when we do that, we get that the slope of the line is 3.15 times 10 to the negative 3rd, which is going to be equal to our rate. Now, because it's 1st order, we should understand that the units there, because it's first order, should be inverse time. And so looking at this, the units here should be minutes inverse, right? That's going to be the value, or that's going to be the units for K. All right. I hope that makes sense. I'm going to pause here. I know that we have half-lives that's going to come up next, but I think this is a good stopping point. So take the time to watch this. Think of any questions that you have, and feel free to ask them in class. Thank you guys for your attention, and I'll see you guys soon.